Today we're going to talk about using convolutional neural nets and LSTMs and deep learning techniques to video. And in particular, we're going to do frame prediction. So this is taking some set of frames from a video and predicting what the next frame is going to be. These techniques are generally applicable. This is our first video on video, I guess, and we can do some more. But I really like this application, even though it's a really, really difficult application. Because I sort of imagine that maybe one day we could use this to automatically generate these videos, or maybe you could imagine putting a video camera on me and predicting where I might go. Now, we're really far from that. Actually, in fact, the useful applications that we have today are really around compression with this video frame prediction. So people really do use it for that. And people are thinking about it a lot because drones and autonomous vehicles, they need a way to actually look at the world through a camera and predict where things are going. Now, one issue with video and why we kind of waited to do this till later in the series is that it requires a ton of compute. And so that's not really fun for a beginner, and a lot of people watching these videos, I know that you don't have access to tons of compute. And so we tried to make a problem for today that would be fun to do even without tons of compute. So we actually talked to our friends at Giphy, the company, and they gave us a whole set of animated GIFs of cats. Now, actually, not all of them really are of cats. These are just videos tagged with cat, but that makes it even more interesting. And the goal is to take a few frames of these animated GIFs and predict the next frame. So even that might seem simple. In fact, you could even just use the last frame to predict the next frame by just guessing it, and it works okay. But even doing this kind of simple task that a human could probably do without too much work, we're going to see is pretty tough for the methods today. So let's jump right in. So let's walk through this notebook on how we're actually going to do video frame prediction. And as always, we make all this code publicly available for you to use and modify. And if you do something cool with it, please let us know. So we start off by going through and importing a whole bunch of files, which we're going to need as we build this model. And we set some hyperparameters, and we load in a data set of cats. So here we're going to use a generator to feed into our fit function. So we go over generators in detail in our data augmentation video, but what this is going to do is instead of loading all of the data into memory, it's going to load the data into memory in batches. So in my generator, we're going to pass in batch size and then an image directory. And the image directory is going to tell us whether we're building a generator on the test data or the trained data. And the batch size is going to tell us how many images or how many videos to load. So this is a Python generator style. And what it does is it sets up input images and output images. And in this case, it actually flattens all the input images into a 96 by 96 by 15 array, where 96 is the image width, 96 is the image height, and then 15 is actually because there's 5 RGB image frames. So there's 15 frames all in a row. And then the output images is going to be 3 frames in a sense, or 1 frame of video where it's RGB values. We actually divide the input images and output images by 255 to normalize all the data to be between 0 and 1. And then we call this yield function. And so this yield is going to return input images, which again is this batch size by 96 by 96 by 15 data structure, and then output images, which is going to be the single frame it wants next, but there's going to be batch size number of them. So there's a matching number of input images and output images. We're also going to set steps per epoch, which is going to be how many steps we take before we check our validation accuracy and validation metrics, and then validation steps, which is how much of the validation data we're going to look at each time that we want to measure our validation metrics. We're going to set a callback here to log the images. And then here I have a little test for our generator. We don't need to necessarily run this, but this might give you a better understanding of how the generator works. So in this case, we set up a generator to have a batch size of 2, and we're going to use the train directory. And then the next line here, we actually call next on the generator. So that's going to return 2 videos and 2 next frames. So videos, as I mentioned, is actually 5 frames of video with RGB values for each frame. And so the shape here is going to be 96 by 96 by 15. And there's actually 2 of these videos and then 2 of the next frame. So we could try calling nextFrame.shape. And you might think about what that shape's going to be. But if we did it, it would be 96 by 96 by 3. If we called next frame 0 dot shape. Maybe we'll just do that. All right, so let's take a look at the data. So we can use the incredibly useful IAMShow command, and we can look at kind of each frame of video that's our input. And then finally, we can take a look at the next frame, which is the video that we're trying to predict. And you can see that in this example, at least, each frame of video is very similar, right? These are successive frames, and so there's not much motion happening. And then this is the final frame that we're trying to predict. So other videos might look differently, and I strongly recommend exploring this a little bit before trying to do a real prediction. Now, one more detail is that we're going to set a function called perceptual distance. And this is because if we just actually looked at the default loss function, which would be the difference between the red values in the pixel and the green values, the green pixels and the blue pixels, it actually isn't exactly how the eye works. So for example, if you get all the blue pixels right, but you mess up the red pixels, that's going to look pretty bad to the human eye. In fact, that's going to look worse than if you got the red pixels right and didn't get the blue pixels right. So there's many different ways to define perceptual distance, but we're going to use a reasonably simple one here, which is kind of based on how the human eye works, but also pretty quick to calculate. So now here, we set up our first model. And so what we're going to do is a 2D convolution on our input. So our input is 96 by 96 by 15. And we're actually just going to take each of those frames, and we're going to do a 2D convolution across all 15 frames with 3-frame output. And we're going to interpret that 3-frame output as red, green, and blue. We're going to do a 3 by 3 kernel, and we're going to set padding equal to same here, which, as mentioned in earlier videos, means that the output size is going to be the same as the input size, so it 0 pads the data. And our input shape is going to be config height by config width, which is 96 by 96 by 5 times 3, which is the 5 frames of 3 RGB values. We're going to compile it and set the optimizer to atom, the loss to mean squared error, and we're going to set this perceptual distance metric as something for the model to return to us as it trains. Then we're going to call fit generator. So fit generator is a lot like model.fit, except that instead of taking in tensors as input, it takes in generators that return tensors. So in this case, we're going to pass in my generator, which is initialized with config.batch size, and then our training directory, so it returns the training input frames and output frames. And then we're going to set steps per epoch, and we're going to divide by 4 here just so that we get more data as the model runs. We could remove this later if we wanted to go longer between checking the validation accuracy. We're going to set some callbacks, image callback and W&B callback, so we can kind of see what's going on. And then we're going to also set the number of validation steps to divide by 4 just so that the model runs a little bit faster. We set the validation data to be a generator, this time initialized with the same config.batch size, but in this case, the validation directory, so that we get the validation images for the validation data. So let's run this and see how it does. So you can follow this link here to see how the model is training. And you can see that the model is getting better, but actually perceptual distance is pretty high. So right now the perceptual distance is at 43. And I actually have no idea what that means, if that's really good or bad. But one thing to look at is the actual output. So here on the left, we have the frame that we were hoping for, and on the right, we have our prediction. And you can see this kind of obviously wrong. It's kind of close, but there's clearly still some weird artifacts. It's more blurry. The colors are different. So it doesn't seem like this model is actually performing very well. So how do we improve it? So one thing that we noticed looking at our input data is that the final frame is actually a pretty good prediction of the output frame. So let's build a model that just takes the last frame in our input and predicts it as the next frame. So here's our Keras model. First, we actually use a reshape layer to change our input, which was 96 by 96 by 15, into 96 by 96 by 5 by 3. So what that does is it actually pulls out each RGB value and kind of puts it in its own slot. So instead of all the RGB values mashed together, we have a little more structure. And what that lets us do is called this permute layer. And so what permute in this case does is it swaps the last 2 dimensions of our data. So the input to this is 96 by 96 by 5 by 3. The output is going to be 96 by 96 by 3 by 5. So now we have 5 sets of RGB values, and we can call this layer, which is a lambda layer, which you may not have seen before. And this is a Keras layer that can do basically anything as long as it operates on tensors. So it actually calls our function slice. In this case, we've defined a little function up here. And what slice does is it slices off the last frame of our input video. So this lambda layer is going to take those 5 frames and it's going to return the final one. So the output shape is going to be 96 by 96 by 3. So this is kind of a funny model. We wouldn't normally think of this as a deep learning model, but we've defined it as a Keras model. So we can actually call model.compile on it. We can give it the same optimizer. We can give it the same loss function, although it's not going to matter because there's nothing here really to optimize. And we can even call fit generator and see how it does. So you can see here that in this graph, right from the start, predict last frame does much better than our 2D CNN model. And we can even go in and we can look at its predictions. And we can see that actually predicting the last frame in many cases is quite good. It's really close to the output frame just because all these frames are in such rapid succession. But now that doesn't feel that exciting. It sort of feels like a CNN model should be able to learn a little bit more. In fact, a CNN model could predict just the last frame with the right kernel. So it's kind of interesting that it was so hard for our 2D CNN model to learn to do this predict last frame. You would think that it would do strictly better, and maybe over time with enough training, it would learn to do this. But we don't have an infinite amount of time, so we want to help our model. So our idea is that we're going to take these 2 models and we're going to combine them. So we're going to make the baseline be predicting this last frame, but then on top of that, it's going to be able to use a convolution model to potentially modify it to get higher performance. So now, in order to combine 2 models, we're going to have to get away from the simpler Keras sequential style and move to a more functional style. And actually, we introduced the functional style in an earlier video on one-shot learning, but here it's going to be really useful to us because we're actually going to try to do in parallel predicting the last frame and a convolutional model. And this is going to make our model work significantly better. So before we add the convolutional model in, I wanted to show how we would take the same predict last frame model and just switch it into a functional style. So this cell here is actually identical to the previous cell we looked at, except it's in the Keras functional style. So instead of calling model.add, we set input to be a tensor, and then we call the same reshape layer on that input tensor. Then we call the same permute layer on the output of the reshape layer, and then we call the lambda layer on the output of the permute layer. And then finally, we set our model in the functional style where we set the input and we set the output as tensors that we've already defined. So this should behave identically to the previous model that we built, and it's good to just check that it does. And you can see that it seems to. The perceptual distance in this case, bounces around a little bit because there's differences in order of the images that get shown to it, but it does seem to be performing identically to the previous model that we built. So now we can make something more interesting. We can actually combine these 2. So now we're going to try to take the convolutional network and we're going to try to take the network that outputted just the last layer and combine them into essentially an ensemble where both methods can make their prediction and we can merge them into a single prediction. And so we do the same reshape and we do the same permute. And then we do the same lambda on the output of the permute layer, but then we also call a 3D convolution, in this case, on the output of the permuted layer. So it might make more sense to do a 3D convolution than a 2D convolution because we're dealing with image data. So the 3D convolution is just like a 2D convolution, but it's going to take in a 3D data structure. In this case, it's going to be the 96 width by 96 height by the 5 frames. And so actually all we need here is a single 3D convolution because it's going to operate on the red plane and the green plane and the blue plane. And then it's going to output a 96 by 96 by 3 by 1 data structure, which we're then going to reshape into 96 by 96 by 3 so we can use it. And then we're going to take that convolution output and we're going to add it to the last layer output. And so what this does, this just sums the last layer and the convolution output reshape. So potentially if the convolution output reshape is all zeros, it's just going to use the last layer. But if there's information in that conv output reshape, then it's going to use that information. So hopefully this combined model will do better than either of the models alone. So one thing that you'll notice when you run this model is that it's a lot slower than just running the deterministic model. So one thing that's clear with our hybrid model, though, is that the validation loss is not as good as the training loss. And so clearly there's some overfitting happening. And we talked a lot about this in previous videos, and we talked about using dropout, which is more common. But actually with video data, it's typical to add something called Gaussian noise. So instead of dropout, which would take some of the pixels and just set them to 0, which you could try, in this case we're going to add Gaussian noise, which is just going to add a random number that's Gaussian distributed with a standard deviation of, in this case, 0.1. And it's going to add that to every pixel. And so in each batch, the noise that it adds is going to be different. And this hopefully is going to help our model learn to be more robust. So this is just the only line that we added. And now instead of last layer being a lambda function on permuted and convolution output be a conv3d on permuted, both of these are called on the noise layer. So you can see that, as expected, the validation perceptual distance is much better than the training perceptual distance, because in this case, in the validation step, we don't actually add the Gaussian noise, which makes the task much harder. But you can see, though, that immediately adding this Gaussian noise actually helps our model. The hybrid model with Gaussian noise is the blue line here, and the model without is the orange line. The 3D convolution, though, can make sense if you have a specific number of video frames, but typically you have a variable number of video frames. And in that case, it probably makes more sense to use an LSTM. But now a standard LSTM wouldn't really make sense on video because the videos actually have a two-dimensional shape. And so there's a layer we can use that's perfect for this situation, which is called a Convolutional LSTM 2D. So this is just like the LSTMs that we talked about in a previous video, but at each step, instead of doing essentially a dense layer, it's doing a convolution. So it's perfect for this video case, and you can actually add it with just one line here, right? So instead of that conv3D, we're gonna use a conv LSTM 2D layer. And it has all the same options as an LSTM. So if we were gonna stack these, we'd have to call return sequence is equal true. And if that doesn't make sense to you, go back to the LSTM video, which is now super relevant for this case. It's only going to actually, in this case, because we didn't call return sequence is equal true, it's only going to return the last output. And then we're going to run that through a conv2D to kind of get it in the shape that we want, which is 96 by 96 by 3. And then we're going to actually combine the convolutional output and the output of just taking the last layer. So this is a very small change, just a 2-line change here, but it actually makes our model significantly more complicated and powerful, and it's going to make it take significantly longer to train. So let's get it started. Yeah, we should get a shot of this cool model. Look at that. Got a conv LSTM 2D followed by a conv 2D. Just adding the outputs. So there's a lot of different places that we could go with this. And one direction we can go is essentially borrowing from autoencoders. So there's a whole bunch of papers out there on video processing, and they use an architecture where they essentially chain together conv LSTM 2D models, at first shrinking the output and then expanding the output. So this kind of combines some of the stuff from many different videos we've done, right? So first we were using this conv LSTM 2D operation, which we explained earlier, which is kind of like an LSTM, but operates on two-dimensional data. Then we use time distributed, which is actually something we introduced in the seek-to-seek video that we did. And we're time distributing, in this case, max pooling 2D, which is going to shrink down the output of these convolutional LSTM layers. Then we're going to do another conv LSTM 2D, and then we're going to do another shrinking down. But then we're going to actually upsample. So we're going to expand out the output of these LSTM 2Ds. So we're going to build this pretty complicated model which has a whole chain of LSTMs, at first shrinking down the outputs and then expanding the outputs. And then finally, we take the output of this complicated thing and we concatenate it with the last layer output, which was a very simple thing of just returning the last layer. And then we use this 2D convolution with a 1x1 kernel. So what does that do? It actually optionally takes the output of just the last layer. Also optionally, it takes the output of our much more complicated model. So this is a good way to fit this particular data, but this video is being filmed in 2019 and things are going to change over time. So one of the things that we did was we actually built what we call a benchmark, and we'll put a link to this in the comments, and we let anyone who wanted to modify this code and model this data. And you can actually look at all the different people that have entered this benchmark and see how well they did. So you can sort it by vowel perceptual distance, and you can see that the different models of the people that actually were able to model this particular cat data the best. And we can zoom in and we can look at the models that they built. For example, this is one of the good ones that we see right now. And we can zoom in and we can see that this person is actually using 3 different strategies in parallel and then concatenating them and then combining them with the conv 2D layer. So one of the awesome things about this benchmark is that you can actually contribute too. So I would love it if you took this notebook, modified the structure of the model, maybe find something that works a little bit better than what I have here, and then submit it back to the benchmark so other people can see what you did and expand on it. Today we're going to talk about applying convolutional neural networks and LSTMs to videos. And we're going to use this technique to generate all the rest of the videos going forward. Sorry, that's so dumb.
Not at all.